The system structure and working principle of the cryogenic radiometer. The system structure and working principle of the U.S. NIST, National Institute of Standards and Technology, HARC, High Accuracy Cryogenic Radiometer, would be introduced as an example. Cryogenic radiometers provide an absolute basis for optical power, flux, measurements at the lowest possible uncertainties. They are used as primary standards for optical power at many other national laboratories as well. A cryogenic radiometer is an electrical substitution radiometer, ESR, that operates by comparing the temperature rise induced by optical power absorbed in a black receiving cavity to the electrical power needed to cause the same temperature rise by resistive, ohmic, heating. Thus the measurement of optical power is determined in terms of electrical power, watt, via voltage and resistance standards maintained by NIST. There are several advantages to operating at cryogenic temperatures, 5 K, instead of room temperature. The heat capacity of copper is reduced by a factor of 1000, thus allowing the use of a relatively large cavity. Also the thermal radiation emitted by the cavity or absorbed from the surroundings is reduced by a factor of 10⁷, which eliminates radiative effects on the equilibrium temperature of the cavity. Finally, the cryogenic temperature allows the use of superconducting wires to the heater, thereby removing the nonequivalence of optical and electrical heating resulting from heat dissipated in the wires. Consequently, most electrical substitution radiometers, including NIST-maintained ESRs, operate at cryogenic temperatures. The Optical Technology Division within NIST presently has two cryogenic radiometers that provide the basis for the spectral radiant power responsivity scale, the NIST designed power, and the L1 ACR. The power is the primary U.S. national standard for the unit of optical power. It has the capability to optimize its configuration for measurements in different spectral regions and for different input laser power levels. For optimized noise performance, it can operate at temperatures as low as 1.7 K for extended periods. The L1 ACR is also an absolute radiometer, but one whose operation is optimized for the microwatt to MW power levels in the UV to near spectral region. In comparison with power, the L1 ACR is compact and mobile, which makes it a convenient instrument to use for scale transfers. The relative combined standard uncertainty of the NIST cryogenic radiometer measurements range is from 0.01% to 0.02% in the visible region of the spectrum. The largest components of the uncertainty are those due to the systematic correction for the Brewster angle window transmittance and the nonequivalence between electrical and optical heating. A comparison between power and the L1 ACR showed that these two standards agreed to within 0.02%, which is within their combined uncertainties as shown in the construction of the NIST primary optical watt radiometer power. The NIST L1 ACR used in spectral irradiance and radiance responsivity calibrations using uniform sources, circus. Comparison of power and the L1 ACR measurements showing the agreement between the ACRs. The error bars are the measurement uncertainty.